Hey Algebra 2, here are the notes for 13.4 Law of Sines Day 2. Now, this is a really tricky day for a couple of reasons. The first one is because triangles don't work like they should. So let's talk a little bit about that. When you have a case like we talked about yesterday with the triangles, we have two angles and a side. There's only one unique solution for that case, because if you know two angles, then you know the third. With the three angles locked in, there's only one way to draw that triangle. However, if you're not given the measures of two sides and the angle opposite one of them, a single solution may not exist. Why is that? Well, if we have the length of this side and this side, I'm going to call them, let's give them some obscure stuff. So x and y. I always know where x is going to be, but y could be here and still touch that other side, or y could be here. So because I know this angle, I know where the sides are at, but I don't know how long this side is. You just know angle, side, side. This is that naughty theorem that they didn't let you use in geometry. And this is why, because we don't know if our y line comes in or if our y line goes out, because it could go either since it's longer than the height. So let's take a look at each case where there's one solution like we looked at yesterday, no triangle where there's no solution, or two triangles where there's two solutions. So let's take a look at each case. In ABC, I'm going to draw it this way. A is 118 degrees. Little a then is 20. And then we'll just do BC. Little b is 17. Angle, side, side. Determine the number of solutions and then solve. Well, we have this table that I'm going to bring over. And this tells me a few things. So if you look underneath each of these triangles, I've labeled them. We have a lot of information, but I want to bring your attention to a few things. The first thing we need to determine is the angle that we have acute or obtuse. Very rarely will it be right. Most of the time it'll be one or the other. Once we know that, we have to do some comparing. And we're going to compare A, B, and this new thing, B sine A. Now what is B sine A? Well, if you think back to our area formula for a triangle, you'll remember that B sine A is just the height of our triangle. So, if I jump back here for a minute, I know I'm jumping back and forth. I know that if my side is longer than my height, I know that it can swing on this vertex at the top. If it's exactly the height, I have a right angle. And if it's shorter than the height, that means it will never fully reach down here. So we could have a side that's much too short, and then the three sides don't match up. That's going to be a case of no solution. So what about this first one? Well, let's use what we know. 118 degrees is our obtuse angle, so we go over here and we use this side. Now we have to compare A and B. So A is 20, B is 17. So if A is greater than B, which triangle is that? Well, it's clearly the one solution triangle. So I'm going to go back here and I'm going to write down one solution. Now that we know how many solutions there are, we now need to determine the number of to determine the other pieces of this triangle that we're missing. In this case, that's B, angle C, and this last side C. And to do that, we're just going to use law of sines from yesterday. So sine of 118, that we know is paired with 20, is equal to sine of B, which we don't know, over 17. Do a little math-a-magic here. Type it into our calculator. 17 times sine 118 divided by 20. And second sine, second answer. And we get that B is equal to 48.6 degrees. And we can then label that on our triangle. I like to do it in a different color if I have one available, because then I know what I've already found and what I still need to find. That one's not going to work. So this B is 48.6 degrees. To find that third one, we just subtract 180 minus 48.6 minus 118. It equals 13.4 degrees. Now that I have that, all I have to do is set up one more law of sines to find my little c. So sine of 118 over 20 is equal to sine of 13.4 over little c. Throw in my calculator. And I find that little c is equal to 5.2. Now let's think about that. Does that make sense? Well, yes it does, because the largest side is across from the largest angle, second largest side is across from the second largest, and the smallest side is across from the smallest angle. So everything works. So I'm also going to go back to this table again. And I see that was type 6. So if I need to come back during my homework and remind myself of what kind it was, I'm going to put a little 6 there. All right, let's keep going. So our second triangle says in ABC, there's your triangle, ABC. A is 50 degrees, little a is 5, and then B is 9. Determine whether it has no solution, one solution, or two solution. So immediately I know it's acute, so I'm going to be using this left side. But I don't really have a great way of comparing A and B because B is bigger than A. So A greater than B, I've got kind of two options here, but really, I need to look between these two. They both could be true because this one doesn't have a B to compare. So before I go on, I have to determine what B sine of A is equal to. I need to be able to compare it. So B sine A is 9 sine 50. When I plug that in a calculator, it's about 6.9 roughly. So if B sine A is 6.9, this tells me that A is less than that value. 5 is less than 6.9. So I don't have any solutions. But let's prove that. Let's show that that's true. Well, if I set up my sine ratio as sine of 50 over 5 equals sine of B over 9, and then I do that math, 9 times sine 50 divided by 5, second sine, second answer, my calculator straight up will not do it. It does not give me an answer because what it says is if this cuts off here, that side length isn't going to be enough to reach. So it can't be done. Even the calculator tells us there is no solution. All right, that was an example of case 1. All right, we've had a case where there's one solution, a case where there's no solutions. That must mean the last one is 2 solutions. So I'm going to right away split up my paper so I can see both solutions. So in triangle ABC, draw it off to the side here. A is 39 degrees, little a is 10, B is 14. We go over to our thing, we see that we don't have the information we need. We don't have B sine A yet, so I'm going to calculate that down here. So B is 14 sine 39, 14 times sine, 14 times sine 39. I get 8.8, which I see is is less than both my B and my A. The only one of these that gives me that option is C, which is 2 solutions. Hey, that's good. We need to see one of those in action. So let's do that. Let's start by just assuming that our triangle is nice, that everything will work out like it should. So sine of 39 is, over 10, is equal to sine of B over 14. When I calculate that, I get 61.8. I then use what I know to do 180 minus 61.8 minus the other angle I have, so I get my C to be 79.2. And then I set up one last trig ratio of sine 39 over 10 set equal to sine of, excuse me, to sine of C, sine of 79.2. Excuse me, I'm really struggling at the moment. 79.2 over C. And when I calculate that, I do sine of 79.2 times 10 divided by that sine of 39. Sine 79.2, I guess I can show you what I'm doing in my calculator here. Sine 79.2 times 10 divided by sine 39. And I get C to be equal to 15.6. But now I realize that B could either be nice in the first quadrant or it could be not quite as nice in the second quadrant. So how do I find out where the reference angle is? Well, let's draw it quick on our unit circle here. If the reference triangle that I'm making and talking about is in the first quadrant here, I know that my second line is in the same spot, has the same reference angle over here. But instead of only going up to this, I have to go all the way over. Well, how do I find what this entire angle is? Since I know the reference angle is 61.8, I can just do 180 minus 61.8 to find out that this angle, so where my triangle side would be in the second quadrant, is going to be at 118.2. So instead of having a angle of 61.8, my B is now 118.2 degrees. My C is now 180 minus 39 minus 118.2, and it's 22.8 degrees. Now this is really confusing. I get that. Totally understand. But just realize we're working with triangles, and if we're working with sine and cosine, it means that sine is going to be the same in both quadrants, meaning our reference angle is the same in both quadrants. So if the reference angle, that B angle, is 61.8 over here, the reference angle is also 61.8 over here. And now I've just swung my original length of my triangle over to the other side. That's what that swinging was doing earlier that we were talking about. All right, let's keep going here. Once we've got that, we set up one final sine because we can find our side C. So we do sine of 39 over 10. We're still okay with that. This time, however, we now have sine of 22.8 over C to find that C side there. So sine, I'll show you what I'm doing, sine of 22.8, close parenthesis, times 10, divided by sine of 39 is equal to C, a length of 6. Let's round it to 2, 6.2. So essentially, I'm going to draw another little triangle over here. We've got two options. We can either have C, I'm sorry, this would be, this is not drawn to scale, so please be patient with me. 10. We could either have a triangle that looks like this with a C of 6.2, or we could have a triangle that looks like this with a C of 15.6. We have two triangles here, and this, my friends, is why we never use the SSA theorem to ever prove anything, because there's just too much going on. So please let me know if you have any questions.